with a little practice, I could tell myself to relax it. Will be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why. Whoopsie, whoopsies, I made a mistake and it's okay. It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsies, whoopsie, whoopsie, whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsie, 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 whoopsie.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo!
It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. I know it's hard to follow the fight's too hard. Wake up, my love, please don't give up on me. It's hard. Wake up.
What is up? What is up, you guys? We are back at it again. Another day here in 100 days of Rootkit. And I feel like my camera is all sorts of messed up. And is this better? There we go. I hope y'all are excited. Today we're going to be talking about data structures. Now, we're going to show our examples off in C, but it doesn't have to be done in C. The overall concept is the most important part, all right? The overall concept of these data structures is the most important part. And these are going to be used pretty much everywhere. When you use things like databases, when you use things like machine learning, when you use things like finding relations or wanting to search quickly through data, this is going to be the way you'll typically be doing it. Now, usually you'll be using a library that's made all this beforehand and it's wrapped up, and you know, you just run the command and auto does it. But we're going to show some of the behind the scenes, right? Behind the scenes logic, because some jobs want you to know these questions. It's not like you're actually going to do them in your job, because most likely you will not, but for some reason they still ask them. So we're going to go over them, all right? Before we get into that though, let's go ahead and finish up with our intro here. If you don't know, we are a Rootkit non-profit org here in the US of A, all right? We are a complete alternative to college and any other boot camp you've seen out there. Not even worth any of the other ones. Colleges, overpriced, waste of your time. They don't teach you anything. You're unhireable for most job positions after college because companies know you don't know anything. Boot camps, straight up, most of them are just a scam. All right, we're not even comparable to them. All right, we are comparable to college on the amount of knowledge you are going to be learning, and we're going to teach you everything and more than you'll learn at college. All right, our certs are the industry's best for a reason. All right, they will help you land those jobs. Additionally, on top of this, all this free stuff we're doing, we have our week 9 giveaway going on. If you go over to the blog section of our site and then click on the week 9, oh, never mind, sorry, the week 10 giveaway going on. That will be live after today's class, all right? You guys can go ahead and enter into that. There's going to be a green button you click, and then you just show that you're subscribed to the YouTube channel, that you're following us on Twitch, very, very basic things, and you can win some of our merch. This drawing is going to happen tomorrow, all right? So let's go and chug along here. If you like what we're doing and you want to help support us, you can click on the link in the description of the video, or if you're on Twitch, you can click in the bio. And there you'll see our charity event, all right? We are a charity, so everything you donate to us is 100% tax deductible, all right? So avoid those taxes. The Gov ain't doing anything good with your money anyways, all right? Trust me, I know. I work for the Gov, all right? Absolute waste of your money. So what you can do instead is donate to us, save those taxes, but also you unlock certain merch, like all of our stickers, the 100 Day of Rootkit exclusive stickers, our Epic Collab t-shirt, and look at this. This is the epic sweater I got on. It's extra thick, extra warm, exclusive 100 Day of Rootkit sweater, has the Rootkit logo on the back. It is epic, all right? Additionally, all donations are being matched 1-for-1 for the first 10,000 donations, and those roll in at the end of the month. And we have pillars along the way, like teaching for 24 hours straight, shaving my head here live on stream, and shaving my beard. Shaving my beard here live on stream. No one wants to see that one, though. So that's our goal, not to hit that goal. All right? Alrighty. Let's go and minimize that and pull the chats back up. How are y'all doing? How y'all doing today? Any questions, comments, concerns before we chug along here on our journey? I guess one last thing. I am in the events chat in the Discord, so if anyone would like to join in, if you are a Patreon or Discord Premium member, you can go ahead and jump in there and chat away, ask any questions that you have, and you'll be good to go. Again, for today's topic, we do not have any test questions on them, on the exam. You will not be affected negatively if you don't know these concepts, all right? You will not fail the practical if you don't know these, or if these don't make sense to you, or you don't memorize them. That's fine. That's fine. We're going over them as a little bit more of a bonus content, all right? For those of you who really want to go, work at the biggest name companies like Google, Netflix, Microsoft, etc., etc. Just know everyone and their dog is applying there, so competition is stiff. You can get the job. You can 100% get the job. Just, you're going to be going against a lot of other people, so you want to make sure that you are in tip-top shape. All right, you got all of your bases covered, so you can shine above the rest. All right. Alrighty here. Let us chug along. And did the music stop? No, it didn't. All right. So let's get on with it. So I'm going to go ahead and open up Visual Studio, and we're going to go ahead and make a brand new project. All right, make a new project console app, and we're going to call this our data structures, and then create. Epic. I'm going to go and delete all this extra crap here. I'm going to remove this include here and replace it with just the C version. So include, and that's going to be std io.h. All right. std, just like the disease. All right. io, input output.h. So data structures. What does that mean? Sounds so fancy, so sophisticated. Should I be paranoid? Should I be worried? Like, is this going to be complicated? The answer is no. No. Data structure is just data, like variables that you've seen, and just ways to use them. Just ways to use them, or maybe put them together and then use them. It's nothing crazy. It can be super complicated if you want to be, or it can be super simple. It's totally up to you. Again, it's just data at the end of the day. You've already dealt with data structures per se in our games. You've made classes. That's a type of data structure. You've made your player. You've made mobs. You've made the drops. That's all different types of data structures, and your programs, executing that. So this is no different. These are just very useful data structure techniques, all right? So the first one we're going to talk about is going to be linked lists. Now again, there are libraries that you can import that will have this stuff already in it, all right? You don't have to make this stuff from scratch. But we're going to go over how it's done from scratch so you have a really in-depth knowledge of these items, and then we'll talk about some of the use cases, all right? So linked lists may sound kind of familiar, lists in there, linked, not sure what that means. Don't worry, all right, it's quite simple. We know that we can make arrays, right? So if I do int and then my array and then say equal to 1, 2, and 3. All right, I've made an array here. All right, I've made an array, and I can get items from that array by doing, my array in like 0 or 1 or 2, etc., etc., etc. Right? It's very, very useful. Very, very useful. This is a very fast operation too. This is what we would call an O of one operation, which means when you want to retrieve data from the array, it's instant. You say which item in the array you want to get the data from, and your computer instantly goes there and instantly gets it. There's no searching, there's no moving around, there's no finding stuff. It's a very, very fast operation. All right, but it comes with some potential limitations because you may not know if the array is, sorted or not, or maybe the data didn't get added exactly where it needs to be added. And, if you say 2 all the time, maybe 2 right now, your index 2 is what you want, but later on it might not be what you want. You might have to do a for loop to go through searching for stuff. There's a potential number of reasons why, arrays might become an issue for you. Maybe you want things to always logically execute in a certain sequence, all right? This is where potentially linked lists can become of value for you. All right, so what are linked lists? You can make linked lists with arrays, but we're going to make them with our structs. All right, with our structs. So remember, to make a struct, it's called struct, stands for structure, and we're going to call this our linked list. All right. There we go. That should be good. So our linked list is just a way of our data being structured, right? It's just normal integers, pointers, stuff like that. Nothing fancy. It's just the way we structure that data together. All right. So how linked lists kind of work is by linking things together. So let's pull up Paint here and show a picture. And there's a couple different types of linked lists. We're going to talk about the two of them. We're going to talk about singly linked and doubly linked. All right. So your array, for example, will, have some data and then have some data and have some data and have some data. And if you ever want, item of index 0, 1, 2, and 3, if you want 1, you can immediately get it. If you say you want item 1, the computer will look right here and be like, I got you. I'll grab it right now. No questions asked. Linked lists are sometimes less efficient than that. So singly linked lists instead will have this data, and it will be in, we usually call them nodes, right? Nodes. It's just something that holds your data. So if this in your array was holding the number 3, and this was holding 4, 5, and 10, these would be kind of like nodes per se. These are pretty much the same. You could have the value 3 in here, 4 in here, 5, and 10. All right, nothing too different. The linked list, though, will also have in the data structure some type of pointer variable that points to the next value in the list. So you basically have a bunch of variables that are like one-offs, like integer variables that are just one-offs, and you link them together into a list. All right, and it's called a singly linked list because you are just pointing to the next item in the list. You're not pointing backwards. It doesn't know potentially how to go backwards. You can only see the forward direction. All right. So again, it's going to be 2 variables on each one of these nodes. One is going to be your data, like the number 3 here. And another one is going to be typically like a pointer. All right. A pointer that will point to where the next node is, whether the next node exists and is alive. Now, this can be extremely useful for certain applications. Like you might be confused why someone might want to use this initially. Because, for example, on a linked list, if I want to get value number 5, or value number 5 here in an array, I'm going to just squiggle that out. This is an O of 1 operation on the array, which means that I say I want item index 2, and I'll immediately get it. For the linked list, this is going to be an O of n operation. Remember, for optimization, you always go based off the worst case scenario. So worst case scenario, I have to go through the whole list to find my items. What do I mean by that? Well, the only entry point we have is looking at 3 here. Once we look at 3, we're like, that's not the number we want. So we go to the next one. And then we're like 4, that's not the number we want. And then we can go to the next one. 5, that's the one that we wanted. We had to go through this one, to finally arrive here. All right, O of n operation, because worst case scenario, we would have wanted like the number 10 or to go to the last item, and it would have taken us the entire time or the entire length of this linked list to get to that data, which is not ideal, right? Not ideal. You're right. It's worse than arrays. Arrays are superior. They are, straight up, when you want to find data directly. But there are use cases for this, particularly for processing data. right? Processing data. And this is the foundation of a lot of machine learning algorithms, but also this is used in what we call binary search trees and a bunch of different trees and graphs, because think of it more like this, all right? This is the foundation of society almost, all right? Let's say you want to make a game or maybe a GPS application where you drive a car, but you can only drive the way you're supposed to in these games, right? You don't want to have anyone doing anything illegal. Well, if these were, let's say, streets telling you, you know, how you could navigate to a location, this would work because you would want to tell people, let me draw out the map right here. So we got like, let's say this is where we're starting. All right, and this is where we want to go. And we got streets everywhere. So we got streets like this. And then these are going to be like one-way streets like this. You know, if you live in certain highly dense population cities, you know, you might have some one-way streets. And then we got maybe another one-way street right here that goes like this. And then another one-way street that goes like this. All right. So if you wanted to give someone, for example, directions on how to get from our green point here all the way over to our red point here, a linked list might be the ideal way to go about it. All right. Because it's directional. All right. It's directional. You can simulate this whole entire road system with a linked list, right? With a linked list. And you can have it so singly linked lists would simulate roads that only go in one direction. So for example, our linked list here could be simulating this one-way road right here, where this is a node, because this right here shows us a cross path, you know, and then this is the link that gets to another node. This is the link that gets to another node. And this is the link that goes to whatever else. All right. And this can be, you know, reoccurring for all of these. And you can connect these together. And when you connect them together in this type of fashion, you know, with every cross section being nodes, this would be what we call a graph, right? But we're getting a little ahead of ourselves. So let's go ahead and just take it back a second and let's go see this in code. All right. Let's go see this in code, because stick with me for these linked lists, because at first they may not seem like they are of any use, but trust me, they are of great use in certain scenarios, right? Only in certain scenarios. This isn't a great thing for everything. So we can have something like data. All right, let's say it's our integer values. We want some integer values. But we did see something particular, all right, when we drawn this out. We have, think of these kind of like, you know, it's not classes, but kind of go back to the concept of classes, all right, where these items right here are going to be edges, and these we're going to refer to as nodes, all right, edges and nodes. And this whole entire thing is your linked list. Now, it's best to break these up in their smallest components if possible, because for example, it's up to you and your use case, but an edge, for example, if nodes are this intersection and this intersection, how long does it take to get from this intersection here to this intersection here? If you're driving, how long does that take? How would you know how long that takes? That's a great question. You may want to, for example, write, you know, physically, if you were writing it, maybe you'd want to write right here that it takes 5 minutes to go from that point to this point. That is potentially information you would want to have as a struct for your edges, where you keep travel time in your edges. All right, travel time in your edges. And maybe at your nodes, left, you have a stoplight. And that stoplight has a, X% chance of having you stop at it. And depending on how long you're stopping at it, you have a X amount of minutes you have to wait at the stoplight. That's information you may want to have here, all right, with your node. So these may be separate items for you, all right, or separate structures that you want to use together, all right. It just depends on how you want to go about making all this. You don't have to break it up as much as possible, but you can if you want. And this whole thing is called a linked list. So knowing that, we're going to make 3 structures, right? We're going to make 3 structures. One's going to be a linked list, which is just going to hold the list itself. The next item is going to be a node, which will just hold some data in the node and then also hold the edge that it's connected to. And then the edge will just be pointing to something and then tell you maybe some travel time or some distance, all right? So if we go in here, we have our linked list. This is supposed to hold everything, which means we may not want, to put an integer value here. Maybe we do, because think of it. How do we know how long this linked list is? If you were blindly standing right here in real life, let me do a different color. If you're blindly standing here in real life and looking down the street, you might be able to see like a couple of stoplights ahead, but you have no clue how long that road goes until you go down the entire road, until you travel down this entire thing. Then you'll know for a fact how many intersections and how long it is, and etc., like that is. So we could, same thing with the computer. It doesn't know that because every time we want to enter the linked list, we have one single entry point, all right? So it might be best for you to maybe store how long things are so you know, so you don't have to figure it out, because the only way to figure it out is to go and travel down the entire road, the entire linked list, which is a O of n operation, and that can potentially be, really long if this is something that holds millions of linked items together. That's going to be a pretty long time. So we're just going to make something in here called, maybe we'll use that size t, which is I think the equivalent of an unsigned long. All right, and we'll just call this the size. Right, this is going to be the general size of our linked list, and then now we need the entry point, the entry node, the one that starts it all. All right, the one that starts it all. This will take us to the node that we first get into, aka our node over here with the data 3 in it. All right, so this one we're just going to, we could call it many things, but this is going to be some type of pointer, and so we know it's supposed to be a pointer. Let's leave a comment here. We know it's supposed to be a pointer, and this is going to be our entry, all right, our entry node, but we haven't made node structures yet. So let's go ahead and make a node structure first, so that way we can actually use the node structure value or data type here. All right, so let's go ahead here and below and let's type struct, and let's call this our node. And then inside of our node here, we want some type of data. All right, so let's just say int, and this will be, I don't know, some type of number. All right, and then every node is potentially going to have an edge. So let's go ahead and say, well, let's leave a comma here because we don't have an edge structure. So we know we want a pointer to some type of edge. All right, something that will take us to an edge, and then we can follow that edge to something else. All right. So next we would want to make our edge, of course. So let's do a struct, and let's do our edge. I feel like I should make these all capitalized, so I'm going to do that. And our edge, we'll just put an int number here too. This will be, I don't know, the travel time. All right, and then this is going to be connecting to a node. That's correct. All right, we're going to connect this to a node. Now we've made the node structure, so we can say here struct node but this needs to be a pointer item. So we'll go ahead and say struct node, and does it need to be right here? Oh, that's what I think that's, no, it's defined before it. Let's see here. Expect the definition of a tag or a name. All right, give me 1 second. I know I'm missing. Oh, wait. That's what I'm missing. Node, and then this will be the node. There we go. I forgot the little name there. All right, there we go. All right, so we're gonna call it like that. Now we have our edge made, so we can do the same thing right here. Say struct our edge, and then edge, and then right here we're always going to enter into a node first, so we're going to say struct our node, and then node. And VS Code likes the asterisk over here, so I'm going to just move it over here. All right, so these are just kind of recreating our items here. The data that you store in them can be anything. We're just putting numbers here, but it could be arrays, it could be photos, it could be entire documents, it could be anything. It's totally up to you guys on what the data is. We're just doing something very simple here. Now, to simplify this even more, if we didn't want to make it more complex with edges here, we could just not include the edges at all, and we could say instead right here, imagine edges in here, right? Imagine it's not here. If we wanted this even more simple, we could just say struct node and then next. All right, so this is just pointing to the next node. All right, so we still technically have an edge, quote unquote, because this is pointing to the next node. So this is our quote unquote edge, but we can't store any potentially useful information in the edge, like how long does it take if we wanted to mimic, roads and how long it takes to travel down a road. We can't store any useful information like that. So this is 100% valid. This is a valid linked list. This just is potentially less useful than if you had a custom edge. All right. So don't get too hung up on the edge concept. You can remove them completely if you want and just refer to the next node. All right, so if we continue on here, we have everything we need here. We have a linked list, we have nodes, and we have edges. Now we just need to generate these items and stitch them together, and then we can give our fully complete example of a linked list. All right, so let's go ahead and down here, and let's say we want to make a linked list. All right, so we're going to say struct linked list my list. All right, so we've created our list, and now we want to make a node. All right, so we're going to mass manufacture a bunch of nodes and then a bunch of edges in the nodes. So we're going to make this, we're going to use a for loop and automatically make like 3 of them and pack them all together, and we're going to use things like malloc, all right, or calloc, to automatically make these, since we're making them dynamically on the fly in a for loop. So if we do something like our for here, all right, we're going to want to make 3 of these. So I'm just going to put a 3 right here. And then inside here, we need to make a node, then connect that node. So I guess it will be, we're connecting each node to next here. And then we got to connect them to edges. All right. So let's go ahead, and the only one-off or weird one would be the first one we create. So let's go ahead and say we want to first always make the node. So let's go ahead and say that we want to calloc 1 times the size of our struct node. All right, we want to calloc that, and this is going to be our temporary node. And we want to be casting this because it's not going to handle void pointers off the bat. So I guess this I got to predefine this one right here. So let's go ahead and just do struct node, and then we'll do an n for these instead of typing out node. Calyx not important, ported, so we need to import it, and that's going to be in standard lib. So let's go ahead and do an include and std lib.h, and we'll go ahead and import that. All right, so now we're manufacturing 3 nodes with Calc right now. 3 nodes with Calc. If we run this, we should see no errors. So let's just run this and see. All right, nothing gets printed out, which is good. We're not printing anything, but the main thing is we don't have any errors. So everything is going good so far. One main issue is we're not freeing everything. We're not freeing all of our Calcs here. All right, we're going to ignore that for right now. We're going to be bad developers, but remember, we need to do our freeing. So what we can do instead, if we don't want to go about it, we can leave ourselves a to-do and say free all the nodes, and then when we make the edges, we want to free all the edges. So we're making our nodes here, and inside of our nodes, we can go ahead and what do you call it? We can go ahead and set a number, right, for its data, and we have these i's that are automatically incrementing in value from 0 to 2 because we're going to less than 3. So they're going to go from 0 to 2. So we can add that to our node. So if we say n and then dot number, not next, number, there we go. And this one's going to be an arrow, not a, no, I feel like this one should, no, I guess it is a number for these ones. Oh, thanks for the follow, Phoenix. So inside here, we can then store the value of I. All right, so we're just storing that data, and it's a little mad at me dereferencing because we need to do our if check. Remember, every time we ask for some allocation from the heap using malloc or calloc, we need to do a check to make sure that we got that, that our request went through. So let's go ahead and do our if return, and does this happy dereferencing null pointer. Do I need to do this? Give me 1 second, y'all. It's been is it not gonna yell at me now? I think it was just being a little delayed there. All right, I think we're good now. The arrow means that we have a pointer object that we have to dereference. It's the same thing as doing like the little asterisks, which my memory's a little fuzzy on this. Again, the whole point is not to really go like ham on being the best C devs ever. It's the concept right now. So we'll see if this is working here in a second. So we're storing our number. Next, we need to do our calloc of our, what do you call it? Our edges. All right. So let's go ahead and make a temporary variable called e for our edges, and then we'll do edge. And then right here, we're going to make our edge. So I'm going to set this to e. This needs to be set to edge. This needs to be set to edge. All right, and then we need to do our check on our edge. Sweet. Once we have created our edge, we can also make the edge's weight, all right, or the number that's inside of it, you know, the travel distance. We can set how long that's going to take with the same logic here with edge. And then is this just called number? It is. And let's just do this with like a +5 on every item. All right, so it'll be, so that way the nodes and the edges are slightly different with the numbers inside of them. Then we need to connect our node and our next to be equal to the edge, right? And this should be, it should just be the pointer by default, right? It's not liking that. Let's see here. What do you not like? Oh, whoops. Let's remove this. this, and it says that the value of edge pointer cannot be assigned to an entity type of node pointer. So did we mess this up? Yep, right here. We're doing a node pointer, not a edge pointer. So let's do our edge right here. All right, so now it's happy, and this is set to next, and that will be equal to our node. All right, sweet. So we have the process set up of mass manufacturing these nodes and connecting them together. The only issue that we have right now is the initial entry point isn't being logged here in linked list, because we're just making this first node, then making the edge, connecting them, and then we're replacing that first node with a new node and adding new data into it. So every time this runs, it's going to replace these variables with brand new allocated memory. We're going to lose access to the data we asked from the operating system. But that's fine. It will not be recovered unless we personally free it. It will just be lost in the ether of your RAM until our program closes and the operating system cleans it up, or if we free it. So the way to make this all usable is we have to make sure we log the initial entry point on our linked list somewhere. So if we go here, and we can just do an if statement right here. If I is equal to 0, so if we're on the first node being created, we want this to be hooked up to our linked list. So we'll say linked list dot node is going to be equal to our node. All right, it's going to be equal to our node. So this way we have the initial node that was created, and that will be our initial entry point. So if we run this now, we should see nothing get printed out. It should just be, it should just run and execute, and it's not. So let's see here. Main function must return a value. Let's go ahead and just do a return 0 right here. Let's rerun this. And what is our next error? Size t to int conversion. Size t. Okay, it doesn't like that this is a size t, and these are integers. So to get the quick way to get around that is we can just say int right here instead of size t. If we rerun this, we got one last error. Main function must return a value, and this return is what it doesn't like. So we'll do a return 1 here, and this one a return 1. Remember, in general, return 0 means everything was a-okay, no issues. Returning 1 or more usually means something went wrong. So let's run this now, and you can see it runs, but nothing gets printed out. We did a lot of work here with no visual feedback, and that's why I was saying, a couple days ago, is that this is why a lot of people like front-end development, right? They like front-end development, JavaScript, stuff like that, because there's a lot of visual feedback and clarity, and it makes it really, really easy for people to get into it, and which is great. That's a great way to get into programming. I didn't understand a lot of programming concepts till I messed around with JavaScript and front-end development, because it was easier to make things click, all right? We're not including too many print statements here because I'm just trying to get through these examples for you guys, because again, these are like the pro gamer move stuff, to help you with the higher end interview processes. So I recommend self-exploration, because we got other stuff we're going to hit on that's more important that our personal partners ask for. But I know some of you guys may not want to work for some of our personal partners for referrals. You guys may want to work at places like Google, Apple, whatever. So this is the extended stuff that they're gonna ask you about. Close this. So printing often will help you visually see what's going on as much as possible. We've created this. We've created this right here, this whole thing in memory. We've created the whole thing. We visually get no feedback. We can't see any of it. So let's see it. Let's see it. Let's make something that lets us see what's going on here. All right. So we can do that by, let me see here. 1 second, because there's node gets created, edge gets created. The edge, we are missing something here. Node is going to be equal to edge, and then this edge needs to by default be equal to null. Is it a capital N? It's all caps. Needs to be equal to null. And then when we come back up here and we make our node, this new node should now be, so this is where we're going to need an else statement on this. And our edge is now going to be equal to not null, but instead going to be equal to the node itself. Okay, sorry, just some last minute things. So we had a bug in the program here where our edges were being created successfully. By default, we want our edges in what they point to be null, which is the equivalent of nothing or 0. And so when we create a new node, we want that edge to now be pointed to that new node. All right. Let's see this more visual, and we'll go through some visual printouts so we can continue forward with our other data structures here. And they all build off of this. All right. They all build off of this. So we're going to be seeing this a lot more moving forward. Let's go ahead and make a function. I'm going to make it right here. And let's call this we'll do void because we're not going to return anything. And we'll do print our linked list. All right. And this is going to take a linked list. So struct linked, what did I, here we go, string linked list. And this is going to just be LL, right? LL for linked list. And all we're going to do in here is we're going to recursively go through this linked list and print out every single item. What does recursively going through the linked list mean? It means that we're going to call the same function within the same function. We're going to be doing more inception stuff, right? More inception stuff. So within itself, we're going to call itself, and it's going to go deeper and deeper and deeper into an inception hole until it hits some type of end, and then it will pop back up to reality. You'll see here in a second. All right. So we're going to do if, and then we're not going to take the linked list because we would have to make 2 functions or add some extra logic. So we're just going to do node and do n for this. If the nodes, if on the node has a next and that edge is equal to null, then we're going to want to return. What's going on here? Great question. Great question. All right, this like next was right here, right? But node, what does that mean? Well, remember, these are all pointers. So the arrows allow us to go to the next item, right? Like we're actually there. To the next item like we're actually there. So when we use an arrow, the arrow, let me do a different color here. We start, that might not be the best color. We start originally here, and our arrow will take us to this edge. So then we're at this edge, and we use an arrow to move us to this next guy right here. All right, and you can do infinite amount of arrows. So what we're doing right here is we're saying we're currently on this node, all right, and we want to look at its edge and see if that edge is connected to anything. All right, see if that edge is connected to anything, which, yeah, I think that should work for the logic that we have. So basically, how this will look here is we're looking at this edge right here, and we're like, hey, edge, are you connected to another node or not? Because if you're not, we don't want to keep printing things out or going down our little rabbit hole. All right, we want to stop and go back up to reality. All right, so technically how our data structure looks is this end node here will actually have an edge, right? It will have an edge, but it won't be pointed to anything. It won't be pointed to another node. So it will have null right here. All right, it will have null right here, which is nothing. So if it sees that, it's like, oh, that's the end of the list. All right, so go back to reality. So let's go ahead and see here. So we want to do our print f here, and we're going to want to print our percent d, and we'll say this is the node value. So we're going to print out the node value, and this is going to be node and then number, and then we'll print out our edge value. So this will be node next. Oh my god, thanks so much, Matt, for that donation. That's what I'm talking about. Very good. Thanks so much, Matt, for that donation. Oh no, I just closed YouTube on accident. Hold on one second. I gotta pull YouTube back up. If you guys have questions, please ask in the chat. You guys are awfully quiet today. So this is where the inception part happens. All right, at the end here, because our function is called print linked list, right? So inside of print linked list, we're actually going to call the function print linked list. So it will infinitely loop within itself, calling itself forever, going deeper and deeper down the rabbit hole. That's what I mean by it's a recursive function, because it will recursively call itself. The only way it will stop doing that and stop, going down deeper and being the equivalent to a while loop is because of this if statement right here, which will return and stop things from happening. All right, this will stop things from happening. This is important because this will run just as intensely as a while loop. All right, this will go for a potentially very, very long time. By default, when you run your program in Linux, Mac OS, or Windows here, they have protections for recursive functions. So they know recursive functions are a normal thing that people do. And to protect things from going insane, where you're going down that rabbit hole forever, usually your compiler will have a soft limit already attached to it that will only allow you to do that inception bit, that recursive bit, 100 times or 1,000 times. And to do it more, which usually you will have to do it more, you'll need to alter that. And I think if you make this in Python also, you'll run into the same issue. I believe there's a recursive tracker that will block your recursive functions from going to a certain point, because it can potentially be a lot more aggressive on your memory than a actual while loop. So we're just calling the same function again, except we don't want this function to run on the same bit of data, right? The same bit of data, the same node. We want it to run on the next node, the next part of the chain, right? The next part of the chain. So what we'll say here is we'll say next, and then next will point to the node. Whoops. There we go. All right, so it's going to run on the next node, all right? The next node. Next is the edge, right? We got node, edge, and then node, right? So this next node is what's going to be ran on. So let's see if we did this correctly. Let's take our print linked list, because this is a separate function outside of our main program. So we got to run it here at the end of our main program to see if everything has worked. And we need to put in an initial node. What's our initial node? It's our initial entry point. And that is going to be held by our linked list right here, my list. So let's put my list right here, and let's say node. There we go. So this is where we're going to start, and it should recursively go through every item in the list and print them out. And then once it's done, it will pop all the way back up to reality. So if we run this, we'll see we get some build errors. This popped up because I clicked on yes there. Let me rerun it again. So let's see here. Uninitialized local pointer variable E is being used right here. E is right there. It is uninitialized by default. Okay, so let's think through this bit a little bit more. Node gets created, edge gets created, edge gets connected to node. Then we need to make the next node and connect that to the edge. Should we be making the edges first? No. We could do previous node. Let me see here. We need the edge. Let's draw this out. All right, let's draw this out. Drawing out is a-okay to do. All right. So if you ever find yourself with your classes, with your data structures, with your anything, draw a picture. Get pens. I have a box of pens because I use a pen for 5 seconds and then I end up losing. All right. So I have to buy boxes of pens because I only get a couple uses out of it before I lose it somewhere in the office. I don't know where. And then have paper near you at all times. I have an entire block of printer paper that I just grab from, and I will draw things like this, right? Draw things. I have stacks of paper of just drawings and other things, notes, etc. Have them, right? Or maybe you like books, all right, like a notebook or something. Use them, all right? Draw pictures so you can help yourself understand. That never really gets much easier per se, all right? You just kind of get used to the things that you constantly do. So those kind of become easier to understand, but new concepts are always difficult to understand, so draw them out. So let's see here. We got our node that gets created. Once our node is created, that's the issue here is with our edge, but then we create our edge, and we're trying to have the node equal to the edge before the edge is fully created. It's initialized right here, but not fully created until down here. I think the easiest way would just be to make the edge first. Node next edge. Node next edge. Let's see here. If we made the edge first, what issues will we run into? We'll run into this issue, so let's run this at the end. I feel like this will run into an issue too. We'll see. Nope, no issue. It ran. Except our printing did not go off. So we do have an issue. And we are printing this. We're printing this. Node next node. Alright, where are my notes? Let me pull them up. Where are we going for this one? This one should work, right? Because we're going too deep too quickly. Let's add more print statements here, shall we? We'll mess with this just a little bit longer and then just continue on with our examples. Let's see here. if one of you guys see the mistake, feel free to point it out. All right, so we got edges, nodes, and we're doing our print linked list here. Let's make sure we actually get into this. So let's just do a print statement here, printf, and see if this goes off. If this goes off, it means we are uninitialized E. So print node. There we go. So we're entering it. We are entering it, and it's being messed up on this if statement here, which means we're missing our final connection here. So I remove that else there. So our node gets created, nodes added to it, we add the number, we make the edge, we give the edge a number, we take that node, we make that node equal to the edge, and then the edge's node equal to none. Then we loop back up to the top, we make a brand new node. I think we just need to have a previous node. Struct node prev node. Node is equal to, or prev node is equal to node. So that way we can do else prev, or if, else if prev node not equal to null, then we're going to have our node, or our node's edge our prev node's edge node equal to node. And what's the issue here? This should probably just be equal to null then by default. And if we rerun this, there we go. Whew. Sweating a little bit there. Sorry you guys about that. I thought I wrote it well the first time through, but I was just missing the one little thing here. The prev node, quick little band-aid fix here. Let's fix our little print statements here so we see stuff outputted a little bit better. And we can remove our ASDF. So now we can visually see from all this torture that we've done, we can visually see what has just happened. We can see we've created a node that has an edge value of 5, and the node itself is 0. Then we've created another node with a value of 1, and then it has an edge value of 6. All right, and then it just ends there. All right, it ends there. Most likely it's because of this right here. So what we can do is we can actually, I think this will work right here if we just do that. So let me rerun this now. There we go. Now we get our whole entire linked list printed out. All right, big journey just to see some underwhelming output go on. So again, what is going on here? What is going on here? Let's bring up Paint and let's just do a quick recap here for our singly linked linked list. All right, this again is for a singly linked list. All right, because it's only one edge pointing forward to the next item. So we have a for loop that will automatically create a node, and in this node it has the value 0. Then it's going to create an edge that's attached to the node. All right, and this edge is going to have the value 5 on it. And then this edge is going to, when it loops back up around, this edge will then be connected to the new node that is created. And this new node is now going to have the value 1 inside of it. And then an edge will be created for that node, and that will have the value 6. Then when it loops back around, a new node will be created, and this will have the value 2. And an edge will be created for it, that then has the value 7 to it. But this edge will be there, it will be pointing, but it will be pointing to null, to nothing at first. Right? And that's why we get this output here, 0, 5, 1, 6, 2, 7. 0, 5, 1, 6, 2, 7. We've successfully made a linked list. And review here, again, let me pull this off to the side. We have our node gets created. Let me put this in green. Our node gets created. After our node gets created, if this is the first time creating a node, we'll add it to the linked list. So it's our entry level node, all right? If not, we're just going to connect it to the previous node that we created. So this, the first time we ran through, was a brand new node. So this is all using pointers. This is why this all works really nicely, is we're using that pointer logic where our node is going to be stored here. All right, the pointer to where this 0 is going to be stored here. Then we're going to add 0 to that node. Then we're going to create a brand new edge. We're going to add 0 plus 5 to that node. Then we're going to have that node be connected to this edge. So at first the node was created and then the edge was created separately. All right. These are connected together because of this right here, our next variable. Our next variable, again, is on the node, and it's just a variable that holds an edge pointer. That's called next. An edge pointer, that's called next. All right? This edge pointer is what then makes these connected together. So we're making the edge equal to the edge we just created, and then this node right here, we're just going to make sure that what it's pointing to by default is going to be null. It's going to be nothing. That's what this line is for nothing. And then we're just storing the previous node we created, this one, away in a variable called prev node, because we're going to replace this variable with a new pointer for a new node that we created. Up at the top here, we create a brand new one. We just create this one right here. So we created this edge. Oops. We created this edge. And now we just created this node right here. All right. We just created this node here and we're storing it in that n variable. So the pointer that was in the n variable for this first guy is just completely destroyed and replaced with the pointer for this guy. This is not removed from memory because it was asked for in the heap. So it still stays in the heap permanently until we free it or our program closes. So we just basically threw out our only way to kind of connect to it. We did store it in the linked list, the pointer to this item in the linked list, but we basically, that's the only way we can get to it now, because n now is equal to this new item we've created. This new item we've created was not the first node. It was, so this logic is going to run. So what this is going to say is the previous node we created, aka this node right here that we just created. This is the previous node we just created. Go to the edge of it. All right, so go to the edge of it. And then what it's pointing to right now used to be null. Change that so it points to this one instead. So that's what this is doing here. We're making it so this node variable is no longer equal to, right here, this node variable is no longer equal to null. It is now equal to the next node. And then this just keeps repeating for infinite amount of times that we want to have nodes get created. Again, this is a very useful data structure in certain scenarios. This is a singly linked list, which means the edges only point down one way. As you can see, these arrow signs I have here, that point, to the next item can only take you forward. There's no way you can kind of start at this node and go backwards. There's no way to do, get the previous node at all because you can only see forward. It's as if you are only looking forward. You cannot look backwards. All right. So this is useful for a lot of reasons, but sometimes you may want to also look backwards. You may also want to look backwards. To be able to look backwards is called a doubly linked list. All right, doubly linked list. Was that a question, Kamal? Because I just saw you wrote that out. Can you read that out loud? The previous node. So we made a node. Let me draw this out. So we made a node, then we made an edge. This will not happen the first time we create a node and an edge. Once we create a node and an edge for the first time, we're going to store off that node we created, the pointer to this node that we created. We're going to sort off into that previous node variable. So that prev node. I'm just writing prev right here. So when we go back up here at the top again, we've just manufactured a brand new node. And now this node is the n variable. All right. So we want to connect these guys together because by default they're not connected together. This is just a brand new node. Whoops. This is just I'm gonna write it right here. This is just a brand new node that was created. These ones are connected together, but this one is a brand new node that was just created with the variable n. And this one is now our previous one. So what's going on here is, since this is not the first node we created, we don't want to store it in my list because this is only for the entry node. So we use this logic instead, which says that the previous node, aka this one right here in green that we just created, this one here in green that we just created, this is our previous node. This previous node, the pointer for it, we want you to go from that node, and then we want you to go to the edge that's attached to it. And the edge that's attached to it has a variable called node. So if we look here at the top, all of our nodes, these circles, have a variable integer and have a variable edge. And this is just a pointer to some edge data type. So when we say next, with that arrow sign, what's happening is we're currently in this node and we did an arrow sign to next, which means take us to the edge. So now we're in the edge here. And edge has a variable called node attached to it, which is supposed to point to the next node. But by default, we have it down here. So by default, when we create it, it's going to be equal to null. It's going to be equal to nothing. So this right now is equal to null. It's equal to nothing. So what we're doing right here is we're saying, hey, jump to the edge, and the edge has a little variable that I want you to jump to. I want you to jump to that variable it has called node, which is currently null. It has nothing in it. I want you to instead stuff this new node pointer in there and replace null instead. So null's being removed, and instead it's finally being fully connected to this next item. Does that make sense, Kamal? It's like the arrow signs and the dots are, I think, good symbols per se. So the reason why some have the dots, so basically my list, and I do a dot. My list, since I'm doing a dot here, it means most likely it's a statically defined variable. So I have it statically defined right here. Like the full thing, we're not calicking or mallicking it. So when we do a calic or a malloc, that's why instead we're using more so the arrow signs. But the arrow signs also visually are great because they show how we're moving along, all right? How we're moving along. It's the equivalent of, again, if the nodes and the edges and the nodes and the edges and the nodes and edges are a little too confusing, then think about more like in real life. You know, like we gave the example of a map. So let's go back to that example real quick. We got a map, and you have just entered a city you've never been at before. So in your brain, you have no clue how to get anywhere. It's brand new. This is a brand new linked list per se, all right? Because you've never been here before. You just were dropped right in the middle of somewhere. You look around and you realize you're at an intersection. All right. That is your first memory. The first place you've been to, that's your first memory. That's the first place you'll be referring to as you explore, because everything that you explore from then on is going to be based off of where you first started. You're going to refer to it from where you first started, right? So when you first drop into this city, you're going to be at this intersection, wherever this intersection is. You'll look forward and you see there's a road in front of you. So you start walking down that road. So what has happened so far is when you first looked around, you noticed you were in an intersection. That was the node being created. Then that's your first initial memory of this. Everything that you explore and find later on will be based off of how far or how far relative to that initial place you were at. So that's why we're adding it as the first item in our linked list, as our entry point of our linked list, because this is our reference point. Then you look forward and you see there's a road. That's an edge. And you start walking down it. You don't know how long it takes to walk down this road till you walk down it. But you walk down it and it took 5 minutes. So that's the number that we're giving to the edge here. Again, the number is arbitrary. You can give it any type of data you want. It's just whatever you need. But you don't know if there's going to be another intersection at the end of this road you're walking down, the edge. So that's why by default we have it equal to null, because this is equivalently saying the edge, the road you're on, is connected to another what? You don't know. You don't know where this road ends or what it's connected to. So we just say null. It's unknown. When you get to the end of the road, you look around and you notice you're at another intersection. That's going to be another node. And that's us looping all the way back up to the top here and creating another node because you've just discovered another node. And this if statement no longer gets executed because this isn't the first one in our memory, right? This is the next intersection we found. So we will remember that in our brain relative to the last intersection. This intersection, I remember, is just up that road. And I can find it because if I go to that first intersection, I could walk forward and then get to this one that I'm just on now. So this is why we say previous node here, because you're like referring back to where you started. You know that this intersection can be found relative to the past intersection because if you walk this road, it will be here. So that's you connecting like the memory in your head together with the directions, aka the nodes being connected. Your previous node, the previous intersection, that road you're on next. What does that road you're on lead to? Well, by default, you don't know, but now we do know. So we're going to make it equal to node. All right, we do now know it's equal to this one. Does that make more sense? And you pretty much just repeat the process back and forth. Hopefully that clarified it a little bit more for you, Kamal. I'm going to keep checking the chat to see if you respond, but I'm going to continue forward with doubly linked. Well, let's take a break actually, because we kind of went a little over time. So I'm sorry about that. We'll talk about doubly linked lists, and then I'll give a quick. We won't get into graphs or trees. We'll get into that on tomorrow, Sunday. So that's our chill Q&A. So we're going to do nothing except just sit around, relax. You guys ask questions, we'll answer them. We'll go through anything you guys want to see. Monday, we'll start talking about trees, maybe hit graphs. But at the end of the day, I'm going to show you guys some machine learning stuff and how this is the foundation of machine learning, but not just machine learning, lots of things. Machine learning is just the most like cool hype thing that people are into right now. All right. So I will be back in 3 to 5 minutes. All right. I'll see you guys in 3 to 5 minutes. Alrighty. We are back to continue our journey through data structures and learning about common data structures that are used in everyday life in programming, whether you know it or not. Now, a reminder, we're making this all from scratch to kind of show off the concepts really in details and how they are kind of simple to do, but you don't have to make this stuff from scratch. There are libraries already made where people wrote this code for you already, and you can just use them. Right? You can just import them in Python, include them here in C or C++. Right? You don't have to make this from scratch. The important thing here is the concepts. Right? The important thing here is the concepts, and for you guys to know them and be able to utilize them. Excuse me. Before we move forward, let's talk about ourselves a little bit. If you're just joining right now, if you don't know, we are Rootkit, a nonprofit here in the US of A. We are a complete alternative to college. We are better than any other boot camp. We are the best comp sci certs you can get out there. Period. All right. We are teaching you everything you need to know for free to get our comp sci cert. Additionally, on GitHub, we have everything listed that you need to know. And search, research, learn. We give you free links to a bunch of YouTube channels that will teach you all these concepts. Because knowledge is power, and we're giving it to you for free 99, not compromising one bit on the quality. All right, not one bit. Additionally, on top of all this free stuff that we're doing, if you go over to our blog, then you can see we got giveaways we do every single week. Week 10 giveaway will be live after today's lesson. Week 9 just finished before today. So we're going to be pulling the winner tomorrow. Mystery item. I don't even know what the item's going to be. We're going to pull it together, and then we're going to pull the winner, all right, live. If you like what we're doing and you want to help support us, you can head over to the link in the description, or if you're watching on Twitch, somewhere in the About Us, you can go over there, and you can then donate to us. Depending on how much you donate, you unlock certain rewards like our stickers, our collab t-shirt, or this epic exclusive 100-day of Rootkit sweater I got here with the Rootkit logo on the back. All donations are matched 1-for-1 for the first 10,000 donations. All right, so every time you donate, it's like you're donating double. We have pillars along the way, like teaching for 24 hours straight, shaving my head here live on the stream, and our goal is not to reach this last goal, but that's shaving my beard here live on stream. No one wants to see that, all right? Again, we are a charity, so all donations are 100% tax deductible. So save on your taxes, all right? The gov doesn't know how to use the money, all right? They are terrible with it, absolutely terrible. They do actually immoral things with your money, like forced spending. If they get an allocated, if companies in the military or in any of the gov branches get, let's say I give them $5 million and they spend, let's say, $3 million of that, and they have $2 million left over, they will find something useless to spend that last $2 million on. It doesn't matter. They will find something just to get rid of that money as soon as possible, because in their mind, if you don't spend it, you won't get the same amount of money next season, because they do every year they get their budget back, all right? So if you don't use it, you lose it. So they don't want to lose it, and they don't also want to lose or get their budget cut for next year, so they'll spend it on useless crap, all right? Absolutely immoral. That's all I gotta say. So instead, evade your taxes, donate here, all right? All right, so let's move along here. We have our edges and nodes created, and we're talking about then you can do it again next year. That's right, because if you were able to do it with a less budget, then you can do it again next year. Yep, exactly. yeah, that's the logic is, oh, you only spent $3 million, you don't need $5 million that we gave you, so here's like 3, maybe 3.5 this time. No, you can't have that. You gotta have as much money as possible. So you gotta spend I'm talking. They'll buy not even like big ticket items. They'll buy like a bunch of TVs or like I don't know, other like stupid stuff, pallets of paper, just to like funnel the money away. Don't get me started, all right? Don't get me started. It's insane. That's all I gotta say. Oh, but we gotta make sure we pass the U.S. tax limit thing or whatever, the loaning limit, because you know we gotta spend more. Trust me, they can cut a lot of stuff and be smarter. It won't affect very much at all. Absolutely insane. All right, moving on from more political ventures, let's go ahead and get back to our coding ventures here, shall we? So we went over linked lists. We talked about them. Now, linked lists, singly linked lists we've gone over. Singly linked, which means there's one direction, one arrow. Effectively, you're traveling one way. It's like a one-way street, and you cannot return on that one-way street. You can never get back. You can only move forward. That's the issue we had here, and that's why we had to store our previous node off, because there's no way for us to refer backwards to the previous node. We have no idea. There's absolutely no way of doing that. It's only a one-way street. You can only move forward. And if you passed the place you were supposed to stop at, you can't just go back. You gotta go all the way back to the first place where you started and do it all over again. You guys played old Mario, or what's like a more like modern version game that does like some punishing logic like that, where you play the game and if you don't win, it will start you all the way back at the beginning of the game. All right, that's effectively what singly linked lists do. All right, if you don't get to where you're supposed to go, or like you missed it, you passed it, whatever, you have to go back to the beginning. This has pros and it has cons. All right, the pros are it's very, very small. These data structures here are very, very small. As you can see, like there's each one of these structures only have an int and then a pointer. So the int's what, 4 bytes, I think we saw, and then the pointer is going to be 8 bytes. So each one of these are going to be 8 plus 4, 12 bytes in size. Technically, it's going to be 16 because of a reason we haven't talked about. Effectively, your computer likes things being nicely organized and arranged by usually 8-byte blocks. So even though sometimes you may only be allocating or need to allocate 12 bytes here, your operating system might make it and pad it off with some extra data to make it more like 16 bytes because it's able to process that data faster. But moving on from that, it's very small. When we add extra complexity to it, it requires more memory, potentially more processing power. It just scales not very well. So doubly linked lists are a way to make this more powerful, but it uses obviously more RAM, right? More RAM, and if you were saving these, it's going to use more hard drive space. Doubly linked lists solve this issues of one-way streets with having an edge that points backwards. Doubly linked, 2 edges, right? 2 edges. So literally, it's that simple. We have our nodes just like we've had before. We can make more nodes like we have done before. We have our edges like we've already done. The only thing we need to do now is make it so we can add a second edge to this node, but this edge is able to look backwards. All right? Look backwards. That's doubly linked lists for you. All right? So we can do that by, so I changed this right here to, instead of next, I changed it to edge. So maybe that will help you guys a little bit. I don't know why I didn't do that in the first place, but now you can see previous node to edge to node. So hopefully that makes a little bit more sense. But now we got to change this from edge to something else because we have 2 edges. We have the edge that goes forward and we have the edge that goes backwards. So we could call that maybe the forward edge and the backwards edge, or we're lazy, so let's just do F edge for the forward edge and B edge for the backward edge. So it's as complex as just copying and pasting this line again and then making it so it's F edge and then back edge. All right. Very complicated. I know. It was a lot of modification we had to do there. Struggled for a little bit, but we made it through. Don't worry. We made it through together. That's pretty much it. now you have a doubly linked list. Of course, we got to change our logic down here below. So we're printing those values correctly, and maybe we need to change some of this logic. Now, for a real world example, same thing, intersection streets, you can use the same example, except now instead of one-way streets, you have just a normal street, a two-way street, you know, where there's traffic going on both sides, and each edge is its own unique variable. So, you know, maybe it takes 5 minutes to travel on this street forward and 30 minutes to travel back that way. Some of you guys have maybe seen traffic before and how one side might be clogged up and the other way is free as a willy. All right. This is the exact same reasoning you would want to use the edges doubly linked lists to kind of show that off. So it takes 30 minutes to go from, I don't know, Atlanta to Houston, but from Houston to Atlanta, it takes 5 minutes. You're going very, very fast. You're on a rocket ship, right? Because of traffic or whatever reason it is. You know, this doesn't have to be traffic. This can be literally anything because it's just data at the end of the day. But yeah, like the snake game. Yes, just like the snake game. Yep, I agree. So to finish this up, we just need to modify our logic a little bit. So we have two edges. So for our print function here, we have two edges now. So let's print both of these edges. We have our back edge and our forward edge. And we want to move forward every time we print. So we'll pass our forward edge onward. All right. And then for this right here, we want to make a node, but our node, after we create it, our node is going to set its forward edge. Forward edge equal to null, and its backward edge equal to null. All right, just some house cleaning stuff. All right, so by default, the moving forward will be equal to nothing. Moving backwards will be equal to nothing. So you're incapable of doing either of them. So later on here in this logic, we'll dictate that. All right. So if this is the first item in our list, so we were dropped in the middle of a city somewhere. If we try to go backwards, we see there's just a brick wall. So it will be null. And if we try to go forward, by default, it will be a brick wall, and so we'll have null. So right now, if we try to go forward or backwards, we can't because we're bricked in. All right, we're in a crazy city. All right, so we have to create some edges here later on in this for loop to finish that up. So this is for our first item. Again, this is for any item after the first one. So any item after the first one, we need to connect the edge up. All right, so our forward edge, because we changed this to our forward edge now. But additionally, we need to make our new node, our brand new node here, be able to look backwards to our previous node, all right, in that previous edge. So if we say our current new node, we want to be equal to our backwards. We want to grab the backward edge, and we want to have that equal to our backward edge and then the node. I think we're gonna have to add a little bit more logic here than I expected. Backward edge, and then this would be equal to our previous node. All right. So we got our new node. Our backwards edge is going to be equal to the previous node. So that way we have the previous node is looking forward to the new edge, and the new edge, the new node is able to look back at the previous node. So completing that double structure here. For our edge here, we need to create two edges now. We need to create two edges. This will be, let's call this EF, which is going to be our, or I guess we should do FE. For our forward edge, This is why some variables in some programs look unintelligible, because they shorthand it like this, like we're doing right now. All right, so we're gonna make this pretty unintelligible if you weren't watching this stream. All right, and this is gonna be our forward edge. All right, and then we need to change our pre-definition for edge here. We need to make another one called our backwards edge. All right, and this is not very happy. We'll go ahead and move forward and deal with that here in a second. So let's go ahead and just copy and paste this, and then we'll change it to backwards edge BE. Copy and paste, copy and paste, copy and paste, copy and paste, copy and paste. And this is going to be backwards edge. And there we go. This should be good. Let's see what this is. Referencing null pointer, previous node equals forward edge. Backwards edge, forward edge. This should be on every new node. I want to make the backwards and forward one. Let's run this and see. Remember, the green is kind of like a warning. It doesn't mean it's not going to work. So let's see if it will work if we just run this. It's not working, so it doesn't like something that we're doing here. So again, we can go through the same debugging statements as we did before. Let's just see if it even gets here. Print F. All right, let's rerun this and we'll see that it's not even getting there. So it's not even getting to the linked list. All right, it's not even getting to the linked list, which is happening here at the end. So something's going awry in here, most likely. Surprised it didn't crash, but let's go ahead and try to resolve this. Dereferencing a null pointer. So it thinks that one of these might be null, which is completely true. So we should be able to resolve that if we do. I feel like it would have been resolved with the edge. Oh, this would make sense because it's going to be null by default. So this needs to be moved downward because by default our node, its edges on the new node are going to be null. So that's why it's unhappy with this one, because the edges by default are going to be null. So let's go ahead and remove this. Will that get rid of this one? Because this should no longer be null. We can add this here at the end. Why is my equals? That equal sign, Visual Studio is dying. What is going on? And I think this one just wants me to add the if statement here. Is not equal to null. There we go. So sometimes it will go away with if statements because it's just saying that this might be null. So it wants me kind of to modify this if statement to not do it unless it's not null, because our program would crash and we want to avoid crashes. So that's just a nice little thing that Visual Studio is doing for us. So if we run this, we can see it's now working. It's now working. So let me go ahead and remove this. And for our backwards stuff, let's go ahead and do, I don't know, times 20. I don't know, just so it's very different than everything else. So if we rerun this, you'll see that our, and I guess we should change our, this is going to be our forward edge value and our backwards edge value. All right, and you'll see here, now we got our node value, our forward edge value, and then our backwards edge value. Then we got our node value, our forward edge value, and then our backwards edge value. And then our node value, our forward edge value, and our backwards edge value. All right, so you can see these are all distinct values So that's a way you can visually see these are all distinct edges that are being created. And you can traverse all of them. Now we're able to look backwards and actually travel back from where we were, right? Travel back from where we were. So that is a huge unlock in potential power that we have. Again, the best thing I can relate to you guys right now, for you to understand why this could be important, would be navigation systems. All right, navigation systems, anything that you use like Google Maps, is going to use something like this behind the scenes. This will be literally this data structure with nodes and edges are going to be running it. All right, this is a very common data structure that runs most things that you utilize every single day of your life. All right. Again, it has shortcomings where, you know, if you have a huge list with a bunch of nodes, again, you can't just like an array go immediately to this item, right? In an array, you can say I want the second index item and go straight to it immediately. No delay, get it, print it out. Awesome, you're done. Linked lists though, whether they're doubly or singly linked, it's only one directional. Now, another way you've seen this be used before in everyday life would be servers and how the internet itself works, right? How the internet itself works. So the internet itself works is you live right here, and then you connect to your ISP, and your ISP has a bunch of routers, and they connect to other ISPs, and then there's the server over here you want to connect to. Now, this is a big problem. If you are right here, this is you, and where you want to go to, right here, google.com, and you are always going to be that initial entry point, that initial node to the internet is going to be your router to the ISP, all right? Just like we have the linked list that has the initial node for entry into the linked list, your ISP is your initial node into the network. The question now is, what's the fastest way to get to the server? That's a good question. And it always changes. Every second of the existence of the internet, every second that passes as we talk here, the fastest way to google.com is always changing because the wires may be more congested at 1 second than others. Who knows what people are Googling? Maybe something's going viral, etc. Maybe the power went out on one of the ISP buildings. Maybe a natural disaster. Things are always constantly happening. So just because something is the fastest way at 1 second doesn't mean it's going to be the fastest way in the next second. Just like traffic on the streets. So everything is mapped utilizing nodes and edges. And from there, it's then computed and figured out at any given time what might be the fastest way to get there. You've drawn node and edges many times before in your life for many different reasons. So for example, if we draw this one out, you know, maybe these ISP servers are connected up like this, you know, and you're getting all of these going down here and these going here, and you don't know who's connected to what because they could be connected all sorts of different people. Let's say this one's connected here and this one's connected here, and then this one's connected here, and these ones are connected together. All right, how do you navigate that? Well, this is going to be your graph or your tree problems, all right? This is going to be more so a graph, all right? And a solution on how to do graph traversal. Graph traversal. You deal with this all the time. Have you ever played a video game before? Have you ever had AIs on that video game, like enemies that were jumping around, maybe following you, etc., etc.? How do they know where to go? Oh, they saw you and walked. Okay, but how? From a programming standpoint, how? Do they just walk straight to you? Well, that doesn't work, because what if you go behind a wall? Are they going to just be at the wall walking forward? Maybe if you're a inexperienced dev that doesn't know much about data structures. Luckily for you, lots of devs are like that. So when you use engines like UDK or Unreal Engine, they will automatically have this stuff programmed. They will have edges and node structures programmed and graph traversal pre-programmed for you by default. You don't need to know this, but if you do, it could be very powerful for you because you can then modify it or use a better algorithm for whatever you're trying to accomplish. Because it is just a graph traversal problem when, when NPCs are wanting to walk to you or fight you or attack you, this is what runs it. This is what runs it. Additionally, it goes even further than that. When we talk about things like machine learning, right? When we talk about things like machine learning uses this. This is all machine learning is. It's the same node graph traversal issue. So we go and Google something like machine learning. Now, machine learning most commonly is going to be known by the average person as artificial intelligence or AI. AI is a very broad term that you should try to avoid as a developer so you can be more proper. Because AI is everything from the AI in your games to the AI in classic Mario to the AI in the original Pong game. When I say the AI in the original Pong game, do you think that's even equivalent to something like ChatGPT? No, they're completely different. ChatGPT falls under machine learning, which is still a broad term because technically it's going to fall underneath deep learning. All right. So how that goes about for the terminology is AI is all of this stuff, machine learning is this stuff, and deep learning is this stuff, right? So you're not wrong to say AI, but you're not really 100% right because you're being very, very broad. And I don't think when you ask or request something from a customer, because I hate the government, I just hate the US Gov because it's ran by a bunch of idiots who ask for AI solutions. When you ask me for an AI solution, I know what you mean. You want something that's doing deep learning. But when you say you want an AI solution, I can give you an AI solution that's like over here. That's basically a Pong AI system. I fulfilled your request. You owe me money. You may not be that happy, but that's what you asked for. So be careful and do your research beforehand on what you ask for. Or people like me will just lose our goddamn mind. So if we do machine learning and we look at some images here, we're going to get a lot of buzzy images. Let's go ahead and do deep learning because this is technically more into deep learning. Let's see if we get some better images here. Here we go. You're going to get images like this. All right. You're going to get images like this. This should look very, very familiar to what we covered because it is exactly what we covered. It is one for one the exact same thing. All machine learning applications from our trained machine learning applications utilizing a neural net, so deep learning applications, I should say, will use nodes and will use edges exactly in the same fashion I just showed you right now. Exactly the same way. All right. Theirs are going to be more optimized for handling GPU compute, but it is the same fundamental thing. ChatGPT is using the same thing that we just programmed right now. You don't need to know about nodes and edges or how to make them in order to do machine learning. But if you do know it, you're ahead of everyone else because you have a deeper understanding, right? A deeper understanding of what's going on under the hood. And they use singly linked and doubly linked nodes, all right? So by default, a lot of machine learning applications will be singly linked, which means that over here in input, I give it a picture to look at. It looks at the picture and the data will move down to the output here, and then it will tell me what the output of the picture is. What is that picture? In more complicated machine applications, which are very much more demanding on you resource-wise, they'll have doubly linked lists, which feeds some of the input from that's pushed down back into other items by going back up those connections. All right, it's all very, very important. It's the fabric of our reality as we know it. All right, it may seem a little weird, a little stupid at first, arrays are so much better, but trust me, depending on what you're trying to do, it's very, very good at doing that thing. All right. So between input and output, there's just 3 hidden layers. In this example, yeah, a lot of machine learning networks are actually very, very simple. Machine learning is one of the highest paying fields for developers right now. Why? It's not hard. It's actually really easy to do. It's insanely easy to do. Actually, like legitimately. The hard thing is knowing how to smash these together correctly. And most of it is just trial and error. It's only now within the last couple of years where people are really understanding what some of this stuff is doing. But in general, the top PhDs all the way up still aren't 100% sure on what's going on. They're effectively just smashing these things together and saying, go learn. Does it work? And then they figure out whether it's a lot of trial and error, right? It's a lot of trial and error. So there's 3 in a deep neural network for each one. So deep neural network is going to have is a network with the nodes and edges that have multiple layers, right? That have multiple layers. So this has 3 layers. You could have 1 layer. You could have 100 layers. It's totally up to you. And how all this works is like the layers don't need to be the same size. You could have some layers that are larger than the previous layers or smaller than the previous layers. It's totally up to you. But the main point, yeah, and technically when you're doing this, it's going to be called deep learning. As you can see here, machine learning is slightly different than deep learning. Deep learning is when you're going to have neural networks. So technically our AI aimbot using YOLO v5 is a deep learning application, right? If you want to be very, very fancy about it and you have experience with deep learning. And it's very easy when you use a machine learning application or library. Like I told you, machine learning libraries, or there are already libraries out there for making nodes and edges, right? When you use a machine learning library, like for example PyTorch, they automatically make those nodes and edges for you. So if we go over to the tutorials just to see some basic stuff here. Here you go. This is how can I get a slightly better example here? These are basically your that's not really your nodes and edges. Can I go, build a neural network. There we go. Here you go. This is how to make your nodes and edges. So this is going to make a bunch of nodes and edges for you. And each one of these are going to be 1 layer. So this is going to be 1 layer. And then you're going to connect it to another layer. What does ReLU mean? This is a, don't get hung up on the term. It's called an activation function, but effectively it's the traffic, right? If we're looking at road traffic, right? If we're looking at road traffic here and we're trying to figure out, what way is the fastest to get where, ReLU is basically, you remember our edges here, where we can have these numbers attached to the edges. ReLU is basically a math equation that's attached to the edges, and it will on the fly compute how heavy it is to get or travel across that road. Right? It will tell you how long it will travel across that road. So, yeah, there's basically everything's pretty much made for you automatically. All right, all you gotta do is just slap these things together. All right, any of you guys can run this. Go to PyTorch, run this example right here, and you can. Congratulations, you've completely made your own machine learning application that will work immediately. It takes a couple seconds to do this one and get it to work correctly. What do you use for the aimbot? When you say the aimbot, think COD. Is there different version web devs use? No. PyTorch and TensorFlow are the two de facto standard libraries for utilization of machine learning. Machine learning is heavily GPU reliant, but you can do it on CPU only. But you're pretty much going to be limited to using PyTorch or TensorFlow. There are a couple other ones, but PyTorch and TensorFlow are going to be the ones you want to use. TensorFlow was the first big one out there by Google. It was great at first, but Google was just being an asshole and didn't really modify it enough to make it easy for the normal developer to utilize. It was using a lot of higher end like language, mathematical terms, etc., etc. Basically the learning curve for it initially is very, very high. So PyTorch came out, which is developed by everyone's favorite, Facebook. All right, developed by Facebook, and it's great. It's very developer friendly because it uses very simple terms to create things, right? You still have to learn some of the terminology, like what is linear? Well, linear, there's line in there, so it has to do something with the line. Flatten is for flattening out things. ReLU, there's no way to... There is still a curve. There's still a curve on learning these things, but it's just as simple as it. This is a 3-layered machine learning model. So that picture that we had, it's this. There's an input layer, which is always going to be there because you have to input something in. There's 3 layers, and then there's going to be an output layer. I think I'm wrong, actually. This is going to be the only hidden layer. This would be your input and your output layer, but I digress. All right. I'm simplifying things a little bit right now, but that's literally the general concept, though. That's the little general concept. You can use this in websites. You can export them. So I can't remember off the top of my head the TensorFlow, the PyTorch version of it, but TensorFlow has their TensorFlow JS. So basically, you can make a machine learning model, then export it to TensorFlow JS, and then have machine learning used in the browser, right? So they got some examples here that you can utilize. So yes, this is the only way you can do it via web stuff. Do not use TensorFlow JS for training a model, right? For training a model. Training a model is very resource intensive. Remember all of, like I told you about the memory efficiency and the processing and doubly linked lists, and training is intensive. Training requires a good amount of hardware, depending on how big it is and what you're trying to do. It can take a very, very long time too. So training is not really something everyone can do. Google Colab, which you can look at, Google Colab is great for people that want to do machine learning and don't have much hardware space. So here's Google Colab. They're basically, Google's giving you server resources at Google and a high-end GPU access that Google owns that you're free to use. It's very limiting, but they have, you know, a bunch of examples here for machine learning that you can get started with. For training. For inference, aka running something, and just getting results, that happens after you have something that's trained, and that's very, very non-intensive. You can do that on a lot of devices. Because what's happening behind the scenes when you're training a machine learning model and then you're using it for inference is basically, where's my pictures here? This is not the picture I wanted. By default, you know, these roads and intersections, these nodes and edges that we have, are, when you first make them, they have nonsensical values. They have nonsensical, there's just something that's put in there by default. It makes absolutely no sense. When you train things, the computer will slowly alter the time travel down these roads or inside of these nodes, right? It will automatically kind of update how fast you can travel down these roads and what turns or allows you to turn some of these roads on and off. It's kind of like the equivalent of, think of like just super hierarchical based society where everyone is extremely discriminated against, and you have a privilege card and you're only allowed to use certain streets and roads, etc., if you have this privilege card. Besides, if you don't have it, then you have to use other ones that may be more shitty, maybe super nice, whatever. Effectively, when you feed it data, it will alter these roads, and these roads will be activated or deactivated based off of what your quote-unquote privilege card says. So if you're poor, you can only certain roads will activate for you. And that's kind of how the road system here in neural networks work. Right? It's mimicked very closely off of the brain, which your brain uses activation techniques also. But yeah, I don't think we're going to talk too much more about this today because we're at time right now. But the main thing is, this is really important on a grand scheme of things. You don't need to know this to get into machine learning. You don't need to know this in order to do GPS stuff, because there's lots of libraries that will do it for you. But if you do know this stuff, you'll be able to ace more interview tests if you're going to apply to, the most popular companies in the world. But additionally, when you are working on systems like this, you'll be able to know what's underneath the hood, how it's running a little bit, and you might be a more powerful dev to potentially go in and modify it because you might feel a little bit more comfortable than someone else, right? So we'll continue this journey talking about trees on Monday, and then we'll see if we get to graphs or not. And then after that, we're going to be back at Python, right? And we're going to chug along. But all right, sweet. Any other questions before we call that a day? And again, tomorrow is chill Q&A. Go and drop your questions if you have any questions. Tomorrow is chill Q&A day. We're just going to be chilling. It's your time to ask questions. All right. It goes as long as you guys want it tomorrow. So it could be very short. It could be very long, but it's your guys' time. So please ask questions if you have questions. I'm going to give you guys like 30 more seconds. All right. I don't see any other questions. If you guys do end up having questions, just go ahead and drop it in the 100 Days Rootkit chat in the Discord. We'll get back to you and answer them. For you guys' challenge today, try to rewrite everything I've done here and maybe mess with it a little bit more. Maybe add, like, instead of just a number here, maybe add some strings that are attached to these nodes and edges. I don't know, just have fun with it. Mess around with it. See what you can do. Maybe you've thought about a good use case for this. I don't know. Just have fun with it. Play around with it. All right? All right, sweet. I'll see you guys tomorrow on the next one.